This is part of the Catapult case series. We're now taking a look at a future state version of the Catapult system. We've recorded current state observations and analyzed the data and found that there's a large amount of variation, and the ball isn't always getting in the spec limits of 95 to 105. So we bring a problem-solving team together and they take a look at ways to implement in future state solutions to reduce that variation and to shift that central tendency to be within the 95 to 105 spec, ideally at the 100-inch optimal nominal center target. And so what I want to do now is I want to walk you over to the future state Catapult and take a look at what this team came up with. Let's go. All right, let's take a look at some of the things that were given to the Acme Toy Company problem-solving team. After looking at the data and understanding and analyzing the data, we came to some root causes, and a couple of the root causes include one, the catapult itself would sometimes slip. Even though that it was attached by these clamps, it would sometimes slip. So one of the future state solutions was not only to tape it down, but to also put a grippy pad underneath, and you'll just have to trust me, there's a little grippy pad underneath there. But then it was also firmly taped down. Another issue that we saw is that there was sticking that would sometimes occur with the ball. So when the ball is placed in its little cup holder, it's easy for it to get stuck if you push too hard. And when you push hard, and that suction creates problems. So one of the new standard operating procedures is and I'm going to zoom in on the ball here. Joe, if you can just bring the ball out for a second. The ball has an equator on it. You can see where the ball, one half of the sphere is attached to the other half. That equator will be placed perpendicularly on the cup and gently set on the cup, not smashed into the cup, to avoid any sort of suction. That's a new SOP. But one of the biggest things for improvement was the creation of this stopper. A lot of teams at first think that the solution is around identifying a particular angle setting to go to, but it's still really hard for the human to always hit that same angle stop. But if you've got a permanent fixed stop, you never have to worry about that. So now, Jill, I want you to, without the ball, I just want you to show folks how that works when you pull it back and use the stop. It can never go past it, always lands right on the stop. It's like a mistake-proof way of always getting to the right spot. Another big source of variation through root cause analysis was related to the way that you let go of the launch arm. Sometimes there's a flick of the finger approach. Go ahead and show what I mean by the flick. Yeah. And that creates inconsistency. We had teams play with different types of releases with straws and strings and whatnot, but in the end, the old crab claw approach works the best, where you use your hands as a crab claw. You bring it down, and once it's at that stopper location, you do one count of one, and then you release with your crab claws, just like that. And with those settings in place, let's now take a look at Catapult data. So go ahead, Jill, and show us how this works. And we'll do our shots, record the data in the future state observations spreadsheet, and have you take a look at what future state performance was like.